So in this tutorial we're going to look at the concept of sample space. Sample space, which is basically the listing of all possible outcomes in any probability situation. And we're also going to look at the idea of a sample space diagram, which has limited uses, but in certain situations can be very useful for calculating probability. So let's start with the idea of problem A, let's call it 2 coins. So we're going to flip 2 coins and see what the possible outcomes are. Okay, well, if we've got 2 coins, let's just draw 2 coins out. Okay, so coin 1, let's say that one's come up a head, and let's say this one's come up a tail. And of course we know that the property of coins is that they have 2 sides, so if that's a head, the flip side must be a tail. The flip side of this one will be a head. So a very simple example, and let's think about it in a slightly different way. Let's think about it as a tree diagram. Now, a tree diagram doesn't always show all possible outcomes. In fact, it rarely does. But in this case, we can think about, well, if we start here, so we haven't flipped it yet. Now, if we flip it in that direction, what will it be? It will be, let's say, a head. So let's say that's a head. Or if we flip it in this direction, it would be a tail. Okay? Now, if it was a head on the first flip it again, and again it could be a head or a tail. If it was a head on the first flip it again, and again the options are head or tail. So in a sense, this is a sample space diagram. It's a way of visualizing all of the possible throws, all of the possible outcomes. However, I think we're stopped short of saying it's a sample space diagram because it's not at all clear what the outcomes are. So what we need to do now is list the possible outcomes, which will be a listing that we call the sample space. So the sample space is when we, so S for sample space, is when we list out all the possible outcomes. We can use a tree diagram like this, but we tidy it up in the form of a list. So we've got, and we usually open curly brackets using set notation here. We can start here with this head, so head, head. The next item in the list will be head, tail. Next item in the list is tail, head. Of course, they can be in any order. And finally, we've got tail, tail. So that is the sample space. That's what we usually mean by sample space. A neat listing separated by commas of all the possible outcomes. And we can say the size of the sample space. Let's just say SS. No, let's just say S. Yeah. Size of the sample space is obviously the number of elements, if you like, that we've got in this set, or the number of possible outcomes. So 1, 2, 3, 4. So the size of the sample space is 4 because the number of possible outcomes is 4. So that's the concept of the sample space. But what about the sample space diagram? Well, as we said, this is kind of a diagram, but it's not a very clear diagram. So what we want to do is draw, in fact, a kind of table or grid, and the grid will show much more clearly the sample space and all the possible outcomes. So the idea of a grid then is we need headers, column headers and row headers. So if I draw here a line going across and down, so we're creating basically what you might call a T-table. If we call this coin 2, and if we call this one coin 1, then we've got coin 1 then is the columns, and coin 2 will be the rows. So coin 1 is either a head or a tail, so those are our headers. Coin 2 again is either a head or a tail. And then the sample space is in this part of the sample space diagram, so we simply fill in the product, or if you like, the combination of head-head in this box here, then head-tail, then tail-head. So order matters when we're thinking of all possible outcomes. So tail-head and head-tail are different. And finally, tail-tail. So that is a sample space diagram, and it helps us in simple probability questions. Because if we list all the possible outcomes, then that gives us the denominator for our probability fraction. So let's have a look at an example. If I said, what's the probability of this event, of flipping with 2 coins exactly one head, of getting exactly one head? What's the probability of getting exactly one head? Then the number of possible outcomes is this space here, and the size of that space is 4. We've got 4 possible outcomes. So we say out of 4, how many of those outcomes do have only one head? Well, not this one, okay, because that's got 2 heads. This does have exactly one head though, and this possible outcome has exactly one head as well. So we can see there are two possibilities of getting exactly one head. So the probability of getting exactly one head has got to be 2 out of 4. 2 out of 4, or 50%, or if we want to use a decimal, 0.5. So for simple probability examples, a sample space diagram can show us very clearly all of the possible outcomes and allow us to pick out those possible outcomes that fit the probability question that we're being asked. In other words, that are desirable or favourable to what it is we're asking. Now, limitations on a sample space diagram are very important. First limitation is that the sample space diagram is restricted really just to 2 events. So it can only be used when there are 2 events. So if, for example, we were flipping 3 coins, so if we were flipping 3 coins, we would have something like this. It would go like that here, but then on our 3rd flip, our tree diagram would be able to cope with that, but our sample space diagram would have to be 3D if it was going to be able to show all the possible outcomes. So it would have to be, I suppose, a cube. And if there were 4 flips, in other words, it kept bifurcating. Now this diagram, our tree diagram, has been able to show us the size of the sample space, all the possible outcomes here, but certainly we couldn't draw a 4-dimensional sample space diagram. So we really are limited to describing, if we want to use a sample space diagram, to describing just 2 events. The second limitation is all of the events must be equally probable. So this really only works when you've got equal probability. So these are going to be independent events, and in a later video we're going to look at the difference between independent and non-independent events. But these are the 2 limitations. Given those limitations though, a sample space diagram can be very useful, and we're going to look at now another application of a sample space diagram, which is going to be 2 again, but this time 2 dice. So what if we wanted to show all the possible outcomes of throwing 2 6-sided dice? So again, if I quickly draw the situation that we're dealing with, I always think a picture kind of helps us just think about what we've got here. So we've got numbered dice Okay, so something like that. And if we're throwing 2 dice, we can think about throwing them one after the other or simultaneously. It doesn't really matter. So let's start with the idea of the tree diagram now. Would the tree diagram be a useful way of thinking about? In this case, let's think about the sum of 2 dice. So if we had 2 dice and we're going to add together the score. Okay, well, we would have to start with 6 possible outcomes, because we're trying to make a diagram where we show all of the possible outcomes. So this will be a 1, 2, 3, 4, 5, or a 6. Okay, and now it gets a bit tricky. We've got a 1. Okay, we've got a 1, a 2, a 3, a 4, or a 5, or 6 if we rolled a 1 with the first dice, and we'd have to do the same all the way around. So let me just see if I can sketch that in very quickly. So we'd end up with something like this. And now at the ends of our branches here, we could write all of the outcomes here. But what our tree diagram is not showing us is the totals. In other words, the score when we add together the 2 dice. So it might be useful and interesting to draw a diagram like this, but I think a sample space diagram properly laid out in a grid is going to be even more effective. So let's have a look at that. Okay, so let's draw a horizontal here. There we go. And again, dice 1. So this is dice 1, dice 2. So let's just write D2. And all the possible outcomes need to be listed on the top here as column headers. And for dice 2, exactly the same. Okay, now let's think about the size of the sample space to start with. With this diagram here, the size of the sample space isn't too difficult. All you do is count all the branches around the outside. Or you could say, well, each of these bunches here are 6, and you've got 1, 2, 3, 4, 5, 6 of them, so it's 6 times 6, which is 36. So there are 36 possible outcomes, permutations you might say, of throwing 2 dice. This diagram shows that very clearly, and this does as well in a slightly different way. It's 6 rows of 6. So again, we've got 6 times 6, giving us the size of the sample space as 36. So both diagrams show that very well, but here we've got the possibility of simply adding them as we go along. So 1 add 1, 2. 1 add 2, 3. 4, 5, 6, 7. Here we've got 2 add 1, so that's 3, and then 4, 5, 6, 7. So it's very easy, in fact, to fill out this diagram. And as we're filling it out, seeing patterns that arise. Uh, 7, 8, 9, 10. And one of the patterns that we might see is we might be interested in is which is the most likely score that we're going to get, and we can see that it's going to be this diagonal here. Since this diagonal is the longest, 7 is the most common score on 2 dice. 6 and 8 are equally probable. 5 and 9 are equally probable. 4 and 10 are the same. There are 2 possibilities of scoring 3, 2 possibilities of scoring 11, and only one possibility, obviously, of scoring a 2, and one possibility of scoring 12. If we added all those together, our total probability ought to be, and will be, 1 or 100%. So laying it out on a grid helps us to really see those probabilities much more clearly than laying it out like this. Let's work on a couple of problems then. Let's say we are asked what's the probability of scoring, let's say we're in a game and we need to score 5 or less. So 5 or less. Again, it would be difficult to look at this and calculate that, but if we look on our grid, it becomes a very easy operation indeed. And what I'm going to do, in fact, is just highlight where we've got 5 or less. So we've got 5 in all of these boxes here. Or less means 4 would count, so 4 would count, and 3 would count, and 2 would count. So if I actually box out all of these numbers, and then we can count them quite easily. This in fact is a triangular number, so if you know your triangular numbers, then it should be something like 6 or 10. Well, we've got 4, add 3, that's 7, add 2, 9, plus 1 is 10. So if you know your triangular numbers, that gives you a little check. But we've got 10 that are very clearly 5 or less, and the number of possible outcomes is the number in the total number in the grid, which is 36. So it was very easy for us to calculate that, perhaps much easier than working with a diagram like this. Simply working with the patterns in here, 10 out of 36 is 5 out of 18, which is, let's just reach for a calculator here, 5 out of 18 is 0.27 if we want it in decimal, 0.27 recurring, in other words, approximately equal to 28%. Okay, so another possibility finally is, what if we are asked what's the probability of scoring then exactly, let's say exactly 9. Again, let's look at our tree diagram, and where have we got exactly 9? Well, here's a 9, and again these diagonals are very easy to pick out, and we've got 1, 2, 3, 4 9s. So we can say probability of exactly 9, so a favourable outcome would be 9. So exactly 9, favourable outcome is 9. We've got 4 of them, so we write in the numerator 4, and the total number of outcomes in the denominator is 36. Simplifying, we've got 1 out of 9, and again, not a fraction that I know very well, so 1 divided by 9 is 0.1 recurring, which is approximately equal to 11%, so 11% rounding to the nearest percent. Now, lastly, we need to just change something that we wrote down here. The size of the sample space, we said, from this diagram here is 36. But if we go back to our sample space diagram now, that shows things in a clearer way, we can see that actually a lot of those outcomes are repeats. Now, the definition of a sample space is that it's a set of possibilities. In other words, there are no repeats when we're listing out the elements in a set. So if we list out the elements in this set, S, in fact, it's going to be a lot less than the number of possible outcomes. So in fact, if we erase, let's just erase this, there we go. So if we instead just write that this gives us the number of possible outcomes, the number of possible outcomes in both diagrams is clearly 6 times 6, 36. But the sample space, when we list out the sample space, doesn't give us anything like that. So instead of writing 3, 3, we're just going to write 3. Instead of writing 4, 4, 4, we're just going to write out 4, and so on, right up to the last possibility, which is 12. So the size of the sample space will only equal the number of possible outcomes when those possibilities are exactly the same. The probabilities are the same, in other words. But because the probability of getting a 2 is much less than the probability of getting a 3, which is less than the probability of getting a 4, and so on, because we've got all sorts of different probabilities, the outcomes are not equally probable or equiprobable, and that means that the size of the sample space will be less than, always less than, the number of possible outcomes. In this case, we've got 12 minus 1, because 1's not possible, so 12, subtract that 1, in other words 11. And our sample space diagram gives us a good way of checking that result. All we need to do is add up the number of diagonals. So we've got, well, the 2 here is one diagonal. If we take that as a diagonal, we've got the 3's diagonals, the 4's. So if we count those up, that comes to exactly 11. So we've got 11 diagonals. So 12 minus 1 equals 11. Correct. Okay. Finally then, we're going to look at what you would do if you were asked to graph a sample space diagram. So we have our sample space diagram for the sum of 2 dice. What would it look like if we were to make a graph? Okay. Well, first of all, let's start with some axes. And now if we number up the axes, what we can do on the vertical axis is we can either list the probabilities, in other words, it would be fractions or decimals on the vertical axis, or in this case, what I'm simply going to do is write the frequency. So if we call this frequency, in other words, it's the number of times a certain number comes up. And let's just number up to 10. Okay. Now on this axis, the horizontal axis, what we've got is the sample space. So we've got the sum of 2 dice. And if we number it up, let's just draw some divisions. If we number it up starting at 1, then the sample space in fact will start at 2, since that's the smallest number that we can achieve. Okay, up to 12. Right, now how many 2's are there? Well, just 1. How many 1's are there? 0, so that doesn't get marked off at all. How many 2's are there? 2. Sorry, how many 2's are there? 1. So if I make a cross here, and now I can just draw a bar or a line, a thick line, up to that point. There we go. And then we've recorded how many 2's there are. Now if we do that again for all of these numbers, we should end up with, if I simply draw those up, there we go, we should end up with a shape. And that shape, in fact, is called the normal distribution. With larger number of dice, we should, in fact, get a bell curve. And when we look at statistics and the normal distribution in statistics, we'll see that bell curve turning up in all sorts of places. Here, we can see that it's something approaching a bell curve, it's simply a triangular shape, so you've got a kind of, I suppose, a kind of pyramid. But as we go to 3 dice or 4 dice, then that will start to curve up at the top here, and it will start to curve back again at the bottom, so that we get this bell curve. So interesting to increase this to 3 dice, 4 dice, 5 dice or more, start to see what's happening to the diagram. But of course, if it gets above 2 dice, then we can no longer use the sample space diagram. So remember, the limit for a sample space diagram is, of course, 2 events.